engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast. This is the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith. And coming up, a landmark report that outlines the generational impact of climate change, the man bitten by snakes and even injected with their venom hundreds of times has provided the key to a powerful new antivenom, and a breakthrough in oven technology that's helping to cook up a revolution in industrial baking.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
First this week, a new study suggests that children born in 2020 will face a much tougher climate future than us older generations. The findings, which have been published in Nature, show that more than half of modern-day kids will live through extreme heat waves that have never been seen before, even as the world cuts emissions. Mark Maslin at UCL is the author of Climate Change, A Very Short Introduction, and he has agreed to take a look at the study for us and its implications.
The take-home message is really reiterating what we've said for the last 20 or 30 years, which is as climate change gets worse in the future, then the next generation will be having to deal with a lot more extreme weather events. Now, they focus on things like heat waves, crop failures, river floods, droughts, wildfires, and tropical cyclones. And what they're trying to do is see what is the difference between now and what they're going to be exposed to in their life when they were born only, say, 5 years ago.
The thing is that the world's a big place, and climate change is going to manifest differently in different places. So how have they captured that?
They've been very sensible. What they've done is they've taken the world as it is and then looked at the risks for children born in different countries. They show that, of course, if children are born in a more deprived country, then they're going to have a much higher chance of being exposed to these extreme weather events. The ones that are poorest, they will be doubly affected because of that impact of poverty.
The headline number that I've seen written about the paper is that a child being born today, roughly, is going to see 2 to 7 times more extreme weather events than, say, you and I, born in our cohort. The point you're making is that as a citizen of the UK, for example, our ability to cope is going to be much, much superior than someone who's in very impoverished circumstances. But nevertheless, it's going to be an impact, isn't it?
So the very rich people that were living in California, their homes were devastated by wildfires. But they have insurance. They have an ability to rebound and to rebuild their lives. And I think that's the key thing, is it's not necessarily the impact of the event, it is whether the people and the society can rebuild quickly enough to minimize the impact. The 2 to 7 number is really interesting because it's partly where you live, but it's also about how rich the area is. Anybody living into the future will basically get more extreme weather events, and these will have bigger impacts, but the bigger the impact will be on those who are most poor. This is nothing new. So this paper is very well researched, but basically says what everybody in climate change has been saying for the last 20 years, which is extreme weather is going to increase, it's going to really impact people, and it's going to impact the poorest most.
What's the purpose of doing research like this if it is just telling us what we can probably predict for ourselves based on what climate scientists like you have been saying for a long time? Why does having these sorts of numbers in front of us help? I mean, is this all about influencing policy?
So I think there's 2 things we have to think about. The first thing is science is always trying to improve. So we're trying to understand how many people are going to be affected, who are most vulnerable, because that's partly to understand the impacts of climate change. We really know that there's going to be huge impacts, but we need to know where, when, and who's going to be affected. The second thing is then If we can then put this in front of policymakers to say, look, your country is going to be really affected, your country is going to be affected by these extreme weather events, I think many of us are hoping that will move policymakers to be more sensible.
Whenever we do modelling like this, because it concerns the future, and as Niels Bohr famously said, forefather of quantum mechanics, prediction's really hard, especially when it concerns the future. We don't know what is going to happen, but we have therefore uncertainties, and we think the worst case scenario will be one thing, the best case scenario will be another. So when we consider between those two bounds, what is the best case scenario that they present for children of tomorrow, and what's the worst case scenario?
The best case is if we keep climate change to the 1.5 degrees. Now, I know that we have just pushed through that for the last 12 months, but if we can either bring it back down or we can actually make sure that we don't get any warmer, then children born in 2020 will be looking at double the risk of extreme weather events into the future. Whereas if we go to sort of like the 2.7 and above degrees warming that we are expecting due to how the politics and economics is going, then you're looking at more like 5 to 7 times the number of extreme weather events. And you have to remember, it only takes one extreme weather event to ruin a person's life.
Confronted with these data and looking at our families as they grow up, what should people be thinking we need to do in order to try to reduce those numbers to the best case scenario?
The first one is we should be reducing our carbon emissions. We should be moving from 19th century burning stuff, fossil fuel driven economy to a 21st century electric dominated, renewable energy dominated society. And that is already starting to happen. We just need to accelerate it. And the problem is there's a lot of backlash happening in many countries like the US, UK, and in Europe's, all trying to go, no, 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 it was great when we were burning stuff and causing air pollution. I don't quite get that. So that's the first thing we need to do. We need to do this as quickly as possible, which you and I have had these discussions many times. It improves everybody's lives because it cleans up the air, it's more efficient, it's cleaner, it's safer, tick, tick, tick. The second thing we have to do is adapt. We have to support the most vulnerable people in every society, not just poor countries, but rich countries that have extreme poverty, like the US and the UK, and work out how we can protect those vulnerable people from extreme weather events.
Mark Maslin at UCL there, and that study he was commenting on has just been published in Nature. And we'll hear a bit later on in the programme, actually, about one new initiative that is striving to decarbonise the baking industry. That's on the way. Before that, though, scientists say the blood of a US man who injected himself with snake venom and exposed himself deliberately to snake bites hundreds of times for nearly 2 decades has led to an unparalleled antivenom. Antibodies found in Tim Freedy's blood have been shown to protect against fatal doses from 13 of the 19 snakes from the group known as elapids, identified by the World Health Organization as being amongst the deadliest on the planet, and they include cobras and mambas, for example. A team at the company Centivax have been able to isolate the genes that Tim's immune system is using to produce these antibodies and use the message they encode to mass produce the same antibodies in the laboratory, bringing us one step closer to a universal antivenom. This is needed because in many places people are often unable to identify what snake bit them, and even if they can, the specific antivenom they often need for that snake might not be available in time to save them. Over 100,000 people a year die this way, and up to 500,000 are left with amputations or lifelong disabilities. I wanted to know what possessed Tim to venture down this path in the first place, though.
I've been into snakes since the age of 5, and that was actually my first bite by a snake. Not really that venomous, rear fang snake, and it scared me. But then I became interested in it. And ever since then, it was going to museums or going to zoos or going out with my buddies herping in high school. Not for anything venomous, because we only have 2 venomous snakes in Wisconsin. So we're basically just chasing colubrids. We're chasing garter snakes and milk snakes, things like that. And then I got into the venomous snakes. I got into cobras.
Tim began buying up these snakes from sources in Florida. He built a special lab in the basement of his home to house them. How many, though? I inquired.
At the max, I had 60.
60? And
Yeah.
what sorts of snakes?
Cobras, mambas.
Just the ones that are responsible for some of the most lethal venoms that we
Yeah,
know of.
yeah.
Yeah. Was
Yeah.
that what fascinated you? Was it the fact that you're dealing with some of the most dangerous snakes, or was there another motivation for being interested in those in particular?
Russell's viper, saw-scale viper, fer-de-lance. Those are the big killers because they live next to people. They just couldn't find them. So I chose the next best thing, which were cobras, which kill a lot of people, and mambas. For me, mambas was my major goal. Half my bites alone, over 100 bites, are just from mambas. They're just so dangerous.
Indeed, about 20 years ago, Tim embarked on a mission to build his own immunity to help solve the snakebite problem around the world. Historically, we've made antivenom by injecting small quantities of venoms into animals like horses and then purifying the antibodies they produce. But it's not perfect. It's expensive, it's time-consuming, and the antibodies are not human, which can in and of itself produce problems. So how did Tim approach the problem to build up his immunity, and how did he administer this incredibly potent venom?
I was accidentally bitten by some cobras when I was milking them, but I was also at the same time injecting venom, so I had immunity.
But why were you injecting the venom?
To build immunity so I don't die.
Did you just do that off your own back then? So you milked the snakes, got the venom, and then you were just shooting up with it?
Yep.
Didn't you think, well, I might die?
Yeah, and I almost did die a couple times.
What, from injecting it?
September 12th, 2001, I had 2 cobra bites back to back in an hour and flatlined. Ended up in a coma in ICU.
But when you injected the venom, how did you know how much to inject? And what on earth was it like when you put it in? Was it painful?
It's very painful. It's kind of like a bee sting, but way worse than that because like bees will yield 1 or 2 milligrams of venom, and venomous snakes can go 400 to 500 milligrams of venom.
Were you using all of the different snake venoms, or were you just focusing on one of your particular snakes at the time?
Yeah, no, not all. Out of the 600, no, not all. I focused on just individual snakes because that way, instead of mixing venom, I know what individual snakes feel like when I'm bitten by them or I inject venom because all snake venom is different.
And it was that very long-term, repeated exposure that's led to Tim's immune system producing a very powerful, very refined, but also very general response to the venom. He now has broadly neutralising antibodies that can bind to many different venoms and block them. And that's what the team at Centivax have worked with Tim to exploit. They've found the memory B cells that make these magic antibodies, and they've copied the DNA recipe, enabling them to produce a product that can block a very broad swathe of the neurotoxin venoms produced by the elapid group of snakes, like cobras. But how does Tim's family feel about what he does? And why does his work actually matter?
They look at it like it's the coolest thing in the world that I'm all over TV or all over the press based on what I do. And they realize that it's important for humanity, for the people that do die from snakebite, that I represent them, even though I'm 8,000 miles away. So that's the way I looked at it, is I'm representing people I'm never going to meet.
So your immune response has enabled the discovery of the genetic code for the antibodies that can neutralise a lot of these venoms now, which is a massive step forward towards a universal venom antidote, isn't it? What will you do next then? Because as I understand it, of the 19 that were tested, you were able to help through what you've done with 13 of those 19, and that leaves a gap of some 6. So is this a question of exposing you to more snakes, or are they going to use a similar approach to then get the final 6 but elsewhere, or from animal studies or something? What's the next step?
Yeah, they just have to pan out my antibodies, and they have to figure out the ones that we need that we don't have right now.
So you are still the source. It's still going to come from you, the solution.
Yeah. Yep, I still give blood. That's my main job, is to give them blood.
That is an extraordinary story, isn't it? I don't think I've ever done an interview quite like that. That was Tim Freedy, and you could say it's a story with real bite.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, Perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith. Still to come, I visit a net zero inspired oven in Cambridge that promises to double the efficiency of the baking process. Now that really is food for thought, isn't it? Before that though, to a breakthrough in the way that we monitor the world's rainforests. For decades, scientists have struggled to measure exactly how much carbon these vast forests store hidden beneath their dense canopies. But that might be about to change. The European Space Agency has just launched a satellite that's capable of peering through the treetops to reveal what is lying underneath. Matt Disney is a leading expert on remote sensing and forest structure at UCL and also the National Centre for Earth Observation.
We've had satellites, and we have satellites at the moment that can do arguably a better job in places here and there and in snapshots, but they can't do it consistently across this huge range: Southeast Asia, Congo Basin, Central Africa, and the Amazon rainforest, of course.
So talk us through where the satellite's going to be parked, for want of a better phrase, so that it can do that comprehensive analysis.
Okay, so it's going to be in an orbit, not parked, so traveling quite fast, but rotating round and around the Earth at an altitude of about 660 kilometers. It goes around the Earth about every 90 minutes or so. And with the Earth sort of rotating underneath it, that's what enables it to build up this picture over time of the tropical forest continent.
So it's going pole to pole, is it?
Not quite, but nearly pole to pole. So it's what we call a near polar orbit. So it's about 10 degrees off polar.
Ah, right. So it's sort of tilted off the poles, and that means that the satellite goes round and the Earth goes round, and that's how you get that comprehensive general cover of everything. How will it be scrutinising the Earth below?
It's using this transmitter on board that sends out radar signals that are using what's called a P-band wavelength. So it's sending out a signal that's about as kind of long as your forearm. And the key thing about P-band is that this signal can go through clouds and it can go through the smaller bits of the top of the forest. So it doesn't get scattered off the leaves and small branches. And then it can bounce off the base of the forest, and it can also then bounce off large trees, the big trees that are 50 or 80 meters tall and contain a lot of the carbon. So it only really sees the big stuff, the big trees in the canopy. And that, again, is this kind of unique thing that this instrument is capable of doing that nothing else we've had so far can do.
Effectively, then, it's weighing forests.
That's right. So by looking at how dense the forests are and how tall they are, then we can get a really, really good idea of how much material there is in there and then how much carbon there is in there.
Different parts of the world have different sorts of forest. Can it deal with both with impunity?
It can, to some extent. The type of orbit and the way it's been designed has been designed to focus specifically on the tropics. And even in the tropics, if you look at Southeast Asia, or you look at the Congo Basin, and you look at the Amazon, they're all tropical forests, but they're all different. So it can do those kind of big forests better than almost any of the other kind of instruments that we have. When you look at forests that are smaller in stature, so shorter and less dense, it does a reasonably good job, but there are other satellites that can do that job better. It's just that they can't do the really tall, dense forests, which is why we've decided to design and build this mission.
How long is it going to take you to acquire all the data? And once you've got it, what are you going to do with it?
It's going to take 6 months in the commissioning phase of the mission. Then it'll take 6 months to check that all the systems are working. Then it's going to take another 18 months before we get our first real global picture from this. And then hopefully the mission will carry on updating that for the next 3 years after it. As soon as we start getting data, we'll be able to get estimates of carbon over large spatial areas, which we just haven't been able to do before. We've been able to get very good estimates in very small locations, and then everything else is kind of trying to fill in the gaps. So the first thing we'll start to look at is building maps of how much carbon there is in these forests and comparing that with what we know already, which we know is patchy and uncertain. Once we have these consistent maps, we're going to be able to start looking at comparing one area of forest to another. So even within the Amazon, the different regions of the Amazon, for example, are behaving in different ways under climate change. So we know that there are areas of the Amazon that have been very strong carbon sinks. They've been taking up carbon and storing it. But because of reductions in rainfall and increases in fire and disturbance, there's large areas of parts of the Amazon that look as if they're turning into a net source of carbon. And so, again, our pictures of that are very sparse and patchy. And so that's a really serious consequence of climate change, if that's true. And then more generally, we're going to be looking at things like deforestation, logging, degradation more generally. Where is that happening? How intensely is that happening? And what are the consequences of that for the loss of carbon and for our ability to make political decisions to finance ways in which to reduce that deforestation and degradation?
Once you've got it up there and it's active and you're starting to get measurements, how do you know it's actually accurate? How do you calibrate this instrument so you can say, yes, the measurement the satellite comes back with actually corresponds to this much tree cover or this much effective forest weight of carbon on the ground? Have you got some kind of standard bit you're going to look at and then compare what you know is there with what it says is there so you know it's right, or you can correct accordingly?
What you're getting at is we have a satellite that's 600 kilometers up in space and it's sending out radar signals. Those are not measurements of biomass at all. It has to go through a whole process of models, and these models are what we turn our observations into estimates of biomass. And we absolutely need to make measurements on the ground to know that the satellite is doing a good job, to validate that product. And so that means going to certain places. So that's one of the projects that I've been involved with, is collecting data from the ground using a whole bunch of other different techniques, but to measure individual trees in 1 hectare plots in places like Malaysia and in Gabon and in French Guiana. And then we're able to say exactly how much carbon is in this 1 hectare bit here. And so once we get an estimate from the biomass mission, we can compare those and say, well, is it doing what it's supposed to be doing? So that kind of ground-based measurement is really, really crucial to the success of a mission like this. It's no use in having consistent maps all across the globe if they're consistently wrong.
We will watch this space, as they say. That's Matt Disney at UCL and also the National Centre for Earth Observation. The UK has committed to achieving net zero greenhouse gas emissions by 2050. As part of this programme, funding's been made available to various industries to drive innovation that might help to push up efficiencies and cut carbon footprints. At the moment, the baking industry relies almost exclusively on natural gas to fuel the ovens that turn out the consumer products that we all enjoy, including things like cakes and biscuits. And therein lies an opportunity. Mark Williamson, an engineer, oven extraordinaire and also fellow of Queen's College in Cambridge, has teamed up with the Ferrero Group, the company behind some of the biggest high street food brands, to break the mould and cook up a revolution in industrial baking. Their new oven technology that they've developed is electrically powered, and it's over 80% efficient, which is at least twice as good as the traditional gas equivalent. It recovers back into the oven much of the energy that present processes currently throw away, and it uses clever tricks of physics to push far more heat into the food than traditional techniques can. Mark invited me to an obscure industrial estate on the outskirts of Cambridge to see their prototype in action.
It's all about net zero and saving energy in industrial baking. That's why you're here.
What is in front of me? We're in a big unit on this industrial estate, and there is a machine. It looks the size of an underground train or a bus in front of me. What is this?
Right, so this is an industrial baking oven, a continuous baking oven, about 30 metres long, and it's actually a baby. The industry has a lot of ovens that are 100 metres long, so although it looks big to you, this is a small one.
And what's novel here? What are you trying to do which breaks the model?
As everybody knows, there's a big drive to get away from fossil fuels, and what we've done here is build an oven that uses renewable electricity to bake food rather than natural gas. In this oven, the first thing that we do is we try to conserve the heat that goes into the continuous conveyor. So this oven has a metal belt that runs through it. It's just over 1 metre wide, and in this case it's about 25 metres long. Once it gets to the end, it comes all the way back again. So it's an endless loop, if you like, of metal.
Effectively a conveyor belt, because I can see it here going round very slowly, end to end. What's it made of?
Okay, so the belt is made of mild steel, which ends up being the right thing for producing this particular type of food, which in this case is biscuits.
Does it make a difference, though, the fact that it's steel, you can embody a lot of heat energy in steel? So are you able to bring, effectively, because it's in a continuous loop, energy from the end of the oven that you'd throw away? Can you get that back to the beginning in some respects and reuse it?
Absolutely, yes you can. To quote some numbers, just because of saving heat in the oven conveyor, we've saved about 30 kilowatts.
Straight away, 30 kilowatts out of what? What would be the normal running consumption of an oven like this?
Right, this oven, when it runs, is drawing about 110 kilowatts, so it's about 25% of it.
Is that why there's a generator throbbing out here? All these cables, are these you?
Yes, they are, yes. We've got a very net zero unfriendly generator outside, giving us 120 kilowatts, because a typical factory unit like this has a supply of only about 35 kilowatts. So.
Good grief. So the biscuits, we can see they come off of the thing that basically presses out rows and rows of biscuits. They end up on the conveyor. There's the steel belt.
Yeah.
Talk us through what happens next then. How do you actually cook them?
Okay, so once the dough is on the steel belt, it goes into a tunnel, which is the oven basically. And inside the tunnel there are heating elements underneath the metal belt and heating elements on top.
Now, when we've spoken about ovens in the past, you've made a lot of the fact that you can use different colours of light, effectively different wavelengths, different energies, to achieve different cooking intensities or effects. So is that happening here?
Absolutely, yes. Heating elements come in all sorts of different shapes and sizes. The cheapest ones, if you look inside your domestic oven and you see the grill, when it's on, it might glow slightly red. That's about 500 or 600 degrees centigrade, and it works in a domestic oven, but it's very limited in terms of what it can do. And specifically, the radiated energy, the color of the light, as you explained it, it actually bounces off food that contains a lot of water. If we get those heating elements much hotter, and by that I mean 1,500 degrees centigrade instead of 500, a lot of the energy magically goes into the food instead of bouncing off.
And is that what you're doing here then? You're by paradoxically making the elements hotter, you actually save energy because more is absorbed by the food, so you use less overall.
Exactly right, yeah.
How do you know, though, what's actually going on in there? Because you're at the stage where you're testing all this out, you've got a proof of concept, and this is government money, isn't it, that are paying to try and cut costs of manufacturing. How do you know, though, when you're doing tests like this, that it's doing what you think it is? What's your readout, apart from the biscuits that emerge at the other end, either cooked to perfection or overdone?
We've got nearly 150 measurement points of temperatures, pressures, flows, all over the oven, and we have something special that's new. We actually have cameras looking inside the oven all the way down it at intervals, and the cameras in real time actually measure the color of the top of the food and the dimension of the food itself. If you put dough into an oven, a biscuit will rise very quickly and get to almost twice its height, and then as it's nearly ready it starts to collapse again. That change in height profile is very useful if you're controlling a process. We don't think anybody else in the world has done this yet.
How else can you save energy, though? Because presumably if you've got an open end to an oven and stuff is going in at a cold end and there's a hot end, there's going to be a pressure difference and air is going to blow through. So how do you not lose all your heat from inside your oven? Or do you? You just have to live with that.
One of the things you have to do in one of these ovens is make sure all the fumes from the baking don't come out into the workspace that's around the oven. So on the roof of the oven there's a series of chimneys, exhaust stacks. And what we do is bring those all together and we put them through what's called a heat recovery vessel. So we spray cold water into the very hot flue gases that might be at 250 degrees centigrade. And what comes out the bottom is hot water that can be used in the bakery for things like washing, keeping chocolate tanks warm with a jacket. Those heat requirements would otherwise require a steam boiler.
If this performs the way that you are hoping, and you get the kinds of savings and heat recoveries that you think you can with this, if it all works, what kind of a difference do you think you could make to the energy bottom line of a big commercial baker?
we were required to do a quite substantial survey of our industry by the government to establish, if you like, the baseline, the benchmark for how the industry performs energy-wise for these big ovens. And the number for that is somewhere around 38 to 40% thermal efficiency.
Compared with
this oven, which we are currently measuring, is at about 82%. And we've got enough data from this test unit that's proved that we've done it, that we can do it.
And if one looks at the size of the industry, what sort of carbon saving might that translate into, back of the envelope?
This oven here uses about 110 kilowatts, and the equivalent amount of natural gas would create about 20 tonnes a day of carbon dioxide.
But the proof is in the eating, and that's not a bad joke. The point is, this is all about food, it's all about flavour, and people are not going to buy something that doesn't taste the way they've got used to it tasting. I hate when manufacturers change the recipe of biscuits that I've learned to love. So does it churn out food that I would not be able to distinguish from a gas-cooked biscuit?
Well, that's a very good question, because food producers are very sensitive to that particular question. They do
as are the customers.
Yes, and they do not want to lose market share. So we've done a lot of work in the lab simulating the heating systems in this oven on a small sort of pilot plant scale, and food tasting panel tests to make sure that we've got a strong belief that we can dial this thing in, basically, to give us food that people cannot tell the difference.
And do you just stop at biscuits? Could you do anything with this, or does it have its limitations?
If you like the physics of this, Chris, the way we're doing it, it has applications right across food, also ceramics, glass manufacture, paper manufacture. All those industries can do exactly what we've done and dial it in, if you like, to their particular product requirements.
Very exciting stuff. Mark Williamson there revealing what he hopes is going to be a net zero win, as well as a breakthrough in oven engineering across many industries. And now it's time for Question of the Week. And this one has certainly got our heads in a spin as James Titko responds to listener Will.
Hello everyone, I recently watched a YouTube video about how Earth would differ if the landmass was rotated 90 degrees so that the Greenwich meridian was the equator and Mexico was near the South Pole. My question is, how would this affect the formation of valuable resources such as coal and diamond, and how would the geopolitical history of the world be affected?
Well, you don't ask much, do you, Will? Only joking. Rotating the landmass 90 degrees westward in the way you're describing would reshape climate zones, ocean currents and geology, and would set humanity potentially on a completely different trajectory. Here to explain is Dr. Alex Farnsworth, Senior Research Associate from the School of Geographical Sciences at the University of Bristol.
Thanks, James. This new configuration, if we consider the United States, Canada and Greenland, would lie entirely in the southern hemisphere now, bathed in very warm, humid, equatorial air. The UK and continental Europe would also become very tropical paradises consisting of dense rainforest, mainly again as a result of this very warm and moist type of equatorial climate that would develop in such a region. Whereas Eastern Russia, India, China and Indonesia would occupy the former sort of Arctic regions, which would be pretty much blanketed in land-based ice sheets. So this has very dramatic implications for global sea level as well. When we consider major ice sheets growing in both hemispheres, more water needs to be locked out and put from the oceans back into the ice. On balance, however, the southern hemisphere's smaller polar land area, compared to the sort of real world Antarctica today, might roughly offset some of this expanded northern hemisphere ice, yielding maybe potentially no net change and very similar sea levels to today. We'd still have deserts forming in such a world. A lot of these deserts are actually formed in what we call the subtropical high pressure belts, where very dry, descending air occurs. With more of the landmass actually sitting under these subtropical arid belts, we might actually see a global expansion of deserts and one vast desert forming all the way from Central Asia to the tip of Africa. Many of today's big major rivers, they may actually end up disappearing. That's all very much dependent on these very big catchment basins of rainfall. You may see no more Amazon River or no more Nile River developing itself.
A tropical paradise in the UK, you say? There's a thought. A lovely snapshot there of the enormous climatic consequences of your thought experiment, Will. But to the second part of your question, What impact would all this have on how natural resources are distributed and on human civilization?
So, if we think about fossil fuels such as coal, oil, gas in this rotated world, these are all formed from ancient organic sediments under specific past climates and tectonic settings. Rotating the continents would relocate or even eliminate today's oil-rich basins. This is such as the North Sea, the Arabian Peninsula region, because those conditions might never even have arisen in the past. If we think about mineral deposits such as diamonds, now these result from processes that are deep within the Earth's mantle. So, as we're the only rotating the tectonic plates themselves, we may likely see them developing in the same places. Specifically, we think about mountain building regions where plates are colliding and forming large mountains, such as the Andes or the Himalaya. We may likely still be seeing these regions as a source of diamonds. Now, if we're thinking about sort of human and hominid evolution, our hominid ancestors thrived in equatorial Africa's diverse rainforest today. In the sort of rotated world, West Africa and Europe would now occupy the sort of equatorial belts, and this might actually be an area that would host early humans. The course of human history would also undoubtedly change. Major civilizations will develop where resources are plentiful and climate is generally stable. With much of Russia now a desert in this rotated world, we may not even see a civilization develop there. Maybe perhaps a more nomadic one that we see in many other sort of desert regions today in cultures, for instance.
So, Will, there are all sorts of implications to your question. Tilting the Earth's landmass in this way would vastly change the geologic, climatic and biological history of everywhere on Earth, and just goes to show the constraints of our geography. Thanks to the amazing Alex Farnsworth for applying his considerable knowledge to this really fun question. Next time, we'll be answering this question from Zhao, who writes in to ask, what happens to the body when you inject stem cells of your own that have been cultivated outside?
And thank you for that, Zhao. And if you have any thoughts on that question, or any of the questions, in fact, that we're discussing, why not head over to our forum? That's at nakedscientist.com/forum. And of course, if you have a question you'd like us to put under the microscope for you, you can drop us a line. It's chris@thenakedscientist.com. That's all we have time for in this episode. Do join us on Tuesday, though, when we're going to be hearing from the space archaeologist Sarah Parcak as a titan of science. You can find out why she earned that name in that programme. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith. Thank you for listening. And until next time, goodbye.